Ethyne molecule. This molecule is also called as acetylene molecule. Ethyne molecule or acetylene molecule. Its formula is C2H2. The X-ray studies of this molecule shows that in C2H2 molecule, 2 carbon atoms are bonded with a triple bond and each carbon is bonded with hydrogen with a covalent bond. The presence of this triple bond in between 2 carbon atoms is evident from the bond energies and bond lengths. Here carbon-carbon triple bond length is found to be 1.20 angstroms, which indicates the presence of triple bond. And the properties which involved also indicates that 2 pi bonds are present in between 2 carbon atoms, because in between carbon and single bond length is 1.54 angstroms, whereas carbon-carbon double bond length is 1.34 angstroms, whereas here the bond length is 1.20 angstroms. Now let us explain the presence of these triple bonds and the structure of C2H2 molecule with the help of this sp2 hybridization. Now here in C2H2 molecule, according to the studies, X-ray studies, it shows that 2 carbon atoms are present as central atoms. 2 carbon atoms are present as central atoms. So the electronic configuration of carbon 1s2, 2s2, 2p2. This is in its ground state. On excited state, this 2s electron will enter into the empty 2p orbital, so that the electronic configuration will become 2s1, 2p3. This is excited state. That means in the valence shell of carbon, we have 1 electron in 2s orbital and 3 electrons in 3 2p orbitals. Now this carbon is involving in sp hybridization. Now once again I will remind you, this hybridization is a hypothetical theory. You should not ask me why only 1 p orbital is take parting and other 2 are not take parting. The structure is possible, structure is true, structure is having experimental evidences. That structure is possible only when this carbon is in this hybridization. So to support that structure, we are proposing this theory. So don't ask me why, when there are 3 p orbitals, only 1 p orbital is involving. Why other 2 are not involving? You should not ask me that question, because I am supporting this. Structure is true. That structure is possible only when 1 s orbital and 1 p orbital will undergone to sp hybridization. Then only the structure is possible. So if sp hybridization takes place in each carbon, so that 2 carbon atoms will have 2 half-filled sp hybrid orbitals. Now this sp hybrid orbital is in this plane. 2 orbitals are arranged like this. Now here we have 2 pure p orbitals which are not take part into hybridization. They are perpendicular to that, because hybrid orbitals are like this, and these 2 pure p orbitals are perpendicular to each other and also perpendicular to that sp hybrid orbitals. Like this. Because one is like this and other one is like this. So these 2 will present like this. So these are the 2 pure p orbitals of this carbon, and these 2 are sp hybrid orbitals of the same carbon. That is the position of each carbon in C2H2 molecule. two half-filled sp hybrid orbitals and two half-filled pure p orbitals are present in each carbon. Such two carbon atoms are there in C2H2 molecule. Now, one half-filled sp hybrid orbital of one carbon atom will overlap with half-filled sp orbital of another carbon atom, and by mutual sharing of a pair of electrons forms C dash C sigma bond. C dash C sigma bond. Now, here in this carbon we have one more sp hybrid orbital. In this carbon also you have one more sp hybrid orbital. They are also half filled with one electron each. These sp hybrid orbitals overlaps with half filled 1s orbital of hydrogen, and by mutual sharing of a pair of electrons forms C dash H sigma bond. Second hydrogen atom 1s orbital overlaps here, and by mutual sharing of a pair of electrons forms C dash H sigma bond. Now, on each carbon there are two half-filled p orbitals. These p orbitals are perpendicular to sp hybrid orbitals. Now, here in this carbon you have one half-filled pure p orbital. Here also you have one half-filled pure p orbital. In this carbon also you have one half-filled pure p orbital. So, the half-filled p orbitals that are present in carbon, which are parallel to each other, they laterally overlaps to form a pi bond. So, this p orbital is parallel to this. So, these two laterally overlaps to form a pi bond. And this orbital is parallel to this. So, these two laterally overlaps to form a pi bond. So, that two pi bonds are formed between two carbon atoms. So, in between carbon and carbon we have two pi bonds, one sigma bond and two pi bonds. The molecule is in linear shape with an angle of 180 degrees. CO2 molecule. This is also another important molecule in which carbon is involved in sp hybridization. The studies, X-ray studies shows that CO2 molecule is in linear shape and two oxygen atoms are bonded with carbon with a double bond, and the bond angle in CO2 molecule is found to be 180 degrees, and the molecule is in linear shape. So, now let us verify how this molecule is formed in the light of this sp hybridization. In CO2 molecule, the atom that present at the center of the molecule is carbon. So, that is central atom is carbon. In any molecule, the shape and its geometry is depend upon the valency electronic configuration of this central atom. Now, the carbon electronic configuration Z is equal to 6. In its ground state, it is 1s2, 2s2, 2p2. That is, in 2s orbital we have 2 electrons, and in 2p orbital we have 2 electrons like this. That is, one empty orbital is present in the valency shell of carbon. On excited state, the 2s electron will move to 2p orbital, so that the electronic configuration is 2s1, 2p3. This is the excited state electronic configuration of carbon. This is on excited state. Now, this carbon will involved in sp hybridization. When carbon is involved in sp hybridization, it forms two sp hybrid orbitals. and these two orbitals in linearly arranged with 180 degrees angle, and both orbitals are filled with one electron each. This is one sp hybrid orbital and this is another sp hybrid. So perpendicular to this, two p orbitals are, one is like this and other one is like this. This is the position of carbon atom. Now oxygen electronic configuration is 1s2, 2s2, oxygen atomic number 1s2, 2s2, 2p4. That is, in the valence shell of oxygen, you have 2 electrons in 2s orbital and 4 electrons in p orbital, 1, 2, 3 and 4. So here we have 2 half-filled p orbitals. These half-filled p orbitals are perpendicular to each other with 90 degrees angle. This is the position of oxygen atom and this is the position of carbon atom. We have 2 oxygen atoms and 1 carbon atom in CO2 molecule. Now let us see how the molecule is forming. Now in CO2 molecule, carbon is in sp hybridization to form, and 2 half-filled p orbitals are also present. This is the position of carbon. Now one oxygen atom, half-filled p orbital, overlaps with sp hybrid orbital of carbon and by mutual sharing of a pair of electrons forms C-O sigma bond. Now in this carbon oxygen we have one pure p orbital with half-filled electron. CO2 molecule, this is another important compound in which carbon is in sp hybridization. CO2, carbon dioxide molecule. The X-ray studies of this molecule shows that in CO2 molecule, 2 oxygen atoms are bonded to carbon atom with a double bond. And CO2 molecule is found to be in a linear shape with bond angle 180 degrees. Let us observe how this CO2 molecule is formed in the light of this sp hybridization. In CO2 molecule, carbon is present at the center. That is, carbon will act as a central atom. We know that the electronic configuration of carbon Z is equal to 6 is 1s2, 2s2, 2p2 in its ground state. On excited state, the electronic configuration of carbon is 2s1, 2p3. That is, in the valence shell of carbon, we have 1 electron in 2s orbital and 3 electrons in 3p orbital. That is, 4 half-filled orbitals are present in carbon atom. Now, 1 2s orbital and 1 2p orbital can only take part into hybridization. Once again I remind you, don't ask me why, because hybridization is a hypothetical theory. The structure of molecule has evidence. There is an experimental proof. So to prove that structure or to get that structure or that structure is possible only when this hybridization takes place. That's why don't ask me why other 2p orbitals are not involving. Since other 2p orbitals are not involving, for that purpose only this molecule is in linear shape. That is the reason. Because why this molecule is in linear? That linear molecule is possible only one s orbital and one p orbital is take part into hybridization. Now, if it was happened. What is the position of carbon in CO2 molecule? When carbon is involved in sp hybridization, you will have two sp hybrid orbitals which are parallel to, which are in a linear shape with an angle of 180 degrees. And two electrons are entering these two hybrid orbitals, so that each hybrid orbital is half filled with one electron each. Now other two p orbitals, they are perpendicular to each other and are also perpendicular to this sp hybrid orbitals. So these two p hybrid orbital, pure p orbitals are like this. This is the position of carbon with sp hybridization. Two sp hybrid orbitals and two half-filled pure p orbitals. Now what about oxygen? Oxygen atomic number is 8. So its electronic configuration is 1s2, 2s2, 2p4. That means two half-filled p orbitals are present in oxygen. These two half-filled p orbitals are perpendicular to each other like this, and they are filled with one electron each. This is the position of oxygen and this is the position of carbon which is involved in the CO2. Now let us observe how those double bonds are formed. Now here in carbon we have two sp hybrid orbitals which are half filled and two pure p orbitals which are also half filled. This is the position of carbon in CO2 molecule. Now oxygen is having two half filled p orbitals which are perpendicular to each other. So one half filled p orbital of oxygen overlaps with half filled sp hybrid orbital of carbon, and by mutual sharing of a pair of electrons forms a sigma bond between carbon and oxygen. A sigma bond is formed between carbon and oxygen. Now in this oxygen, one more half filled p orbital is there and it is also having one electron. Now this p orbital is parallel to the pure p orbital that was present in carbon. So these two p orbitals laterally overlaps to form a pi bond. The second oxygen atom overlaps with the sp hybrid orbital of carbon in the other side, and here also in this oxygen we have one more half filled p orbital, and this is parallel to second pure p orbital that is present in the carbon. These two orbitals laterally overlap to form a pi bond, so that in between carbon and oxygen two sigma bonds and two pi bonds are formed like this, and the molecule is in a linear shape with bond angle 180 degrees. sp3 dehybridization. This is another type of hybridization in which one s orbital, three p orbitals and one d orbital are take part. So the hybridization in which one s orbital, three p orbitals and one d orbital, this is d, three p orbitals and one s orbital. So that means total 1 plus 3 plus 1, that means 5 orbitals are take part into hybridization. One s orbital, three p orbitals and one d orbital. Total 5 orbitals are take part into hybridization. One s orbital, three p orbitals and one d orbital mixed together or hybridized together to form 5 identical hybrid orbitals is known as sp3 dehybridization. What is sp3 dehybridization? One s orbital, three p orbitals and one d orbital of an atom mixed together are hybridized together to form 5 identical hybrid orbitals is known as sp3 dehybridization, and the orbitals are called as sp3 d hybrid orbitals. sp3d hybrid orbitals. These 5 sp3d hybrid orbitals are in planar trigonal shape. That means out of 5 hybrid orbitals, 3 orbitals are in one plane, 1 orbitals, 2 orbitals. This is one orbital and this is another orbital, and third one is like this. They are in one plane, 3 orbitals are in one plane, and other 2 are perpendicular to this. That means 3 hybrid orbitals are in one plane and other 2 are perpendicular to this, like this. So the angle between these 3 orbitals is 120 degrees, and angle between this and this orbital is 90 degrees. That means here you have 2 types of angles. These 3 orbitals angle is 120 degrees and other 2 are 90 degrees angle with these 3 orbitals. So the shape will be trigonal by pyramidal shape. Trigonal bipyramidal shape. The molecule is in trigonal bipyramidal shape with an angle of 90 degrees and 120 degrees. sp3 dehybridization. 1 s orbital, 3 p orbitals and 1 d orbital mixed together or hybridized together to form 5 identical hybrid orbitals is known as sp3 dehybridization, and the orbitals are called as sp3d hybrid orbitals. Out of 5 sp3d hybrid orbitals, 3 orbitals are in one plane with 120 degrees angle, and other 2 orbitals are perpendicular to that plane. That means 2 types of angles will be formed here. They are 120 degrees within the 3 orbitals, 120 degrees, and other 2 orbitals with 90 degrees. The total shape is said to be trigonal bipyramidal shape. Trigonal bipyramidal shape. The angles are 120 and 90. The molecule which take part in this type of hybridization is PCl5. The PCl5 molecule, one phosphorus atom is bonded with 5 chlorine atoms. One phosphorus atom was bonded with 5 chlorine atoms. For this is phosphorus. 3 chlorine atoms are bonded with phosphorus like this. They are in one plane and the angle is 120 degrees. This angle is 120 degrees. All these are in one plane. There is no bond. These dotted lines shows that all 3 bonds are in one plane. There is no bond between Cl and Cl. Don't get confused. If the dotted lines indicates that 3 bonds are in one plane. And other 2 bonds are perpendicular to that plane. That means one is like this and other one downwards. So, this is phosphorus, one Cl, another Cl, and this was other Cl. They are in one plane with 120 degrees angle, and 4th Cl is like this and 5th Cl is like this. So, the bond angle between this Cl with this Cl is 90 degrees, whereas in between these 3 is 120 degrees, and with this also 90 degrees. Now, in one plane, this is trigonal, top one atom is there, you have 3 faces which gives a pyramid shape, and downward another pyramid. That means 2 bipyramidal means 2 pyramids. So, this molecule is in trigonal bipyramidal shape. trigonal bipyramidal shape. Here phosphorus electronic configuration, phosphorus atomic number is 15. So its electronic configuration is neon 3s2 3p5. 3s2 3p3. That is, in the valency shell you have 2 electrons in 3s orbital and 3 electrons in 3p orbital. On excited state, the 3s electron will move into 3d level. In third energy level we have 3d orbital. In third energy level we have 3d orbital. So on excitation this electron will enter into empty 3d orbital. So the electronic configuration will become 3s1 3p3 3d1. Now 3s orbital, 3p orbital and 3d orbital. Remember, here you may have one doubt. In normal electronic configuration, after filling up of 3p orbital, the electron will enter into 4s orbital. 4s is the next energy level. But here, during excitations, that is, the excitation is influenced by other elements. In such cases, the regeneration or degeneration of orbitals will take place, so that 3d orbital will have less energy than 4s. That's why in excited state the electron will enter into 3d orbital. So you should not link this with the Aufbau principle and n plus L rule and all these things. On excited state 3d orbital will have less energy than 4s orbital. So here we have one half-filled 3s orbital, 3 half-filled 3p orbitals and 1 half-filled d orbital. They will undergone to sp3d hybridization, and when 5 electrons enter in these orbitals, all 5 orbitals are filled with 1 electron each. So that here you have 5 orbitals. These are in one plane and third one is like this. All are half filled with 1 electron each. Now in chlorine you know that in the valence shell of chlorine we have one half filled p orbital. So half filled p orbital of chlorine will overlaps here to form p dash Cl sigma bond. And another chlorine atom overlaps here to form another p dash Cl sigma bond. And third chlorine will form some more bond. This is p dash Cl. And here one chlorine atom will form. This is p dash Cl. And you will have another p dash Cl bond. So that 5 p dash Cl bonds are there. Out of the 5 bonds, 3 bonds are in one plane and other 2 are perpendicular to this. Now in PCl5 molecule, remember, in the valence shell of phosphorus, we have 5 pairs of electrons. That means 10 electrons are present in PCl5 molecule. In PCl5 molecule, the valence shell of phosphorus contains 5 pairs of electrons or 10 electrons. This is, we call it as a extended octet rule. According to octet rule, atoms will take part into the bonding to get 8 electrons in the valence shell. But here in this molecule, after formation of molecule, the central atom's valence shell is having 10 electrons, that is 5 pairs of electrons. These molecules which are having more than 8 electrons in their valence shell are said to be extended orbitals or extended octet rule.